Hello, everyone. A new IITT talk. This time it's going to be amazing. As usual, we we passed the 30th. I think we're the 31st lecture with TC205. I'm going to introduce the speakers. I will share my screen. So safety and serviceability in geotechnical design. We have 5 experts from around the world, renowned and young industry, academia. We're going to start with the chair of TC205, Professor Richard Bathurst from Queen's University in Canada. Is going to introduce TC205 and show us some of the activities, very active TC, and talk about reliability design and LRFD for reinforced soil structures. From Argentina, currently in Spain, we have Alejo Sfriso, Dr. Sfriso from the industry with SRK Consulting. And he's going to say time to leave, factor of safety behind. Trevor Orr, Trevor Orr from the University of Dublin in Ireland, a TC205 member also, spatial variability and the selection of ground property values for geotechnical design, very important subject. And from India, we have our junior fellow in research, the role of geosynthetics in the safety and serviceability of geotechnical design. TC205 speakers, we're all ears. I'm going to stop sharing and give the floor to our first speaker, Professor Bathurst. The floor is yours, Richard.
Okay.
Please, for the others, if you mute so we don't have background noise.
Okay, 1 second. Can you see my screen?
All good.
Okay. Thank you, President. And I'm going to start with an introduction to TC205, its mandate, and its recent activities. And then I will give a brief presentation of my related research within the context of the mandate of TC205. Okay, I'm trying to click. Here we are. So the best resource to understand the mandate of TC205 safety and serviceability is to go to the website of our committee, and this is what you see when you click on the link to our page. Broadly speaking, the mandate and the aims and scope of TC205 are shown here. Limit state design, load and resistance factor design, development and assessment of design codes, and the impact of natural hazard on safety and serviceability in geotechnical design. So that's the overview mission of this committee.
Richard, did you mean to share your screen? Because we're not seeing your slides.
Okay, I was trying to do that. Let me try again.
Yeah, I think you're on the second slide now.
Yeah, or slide 4. So can you see it?
Yes. You want to restart or it's okay?
I'll just go back and just.
Yes.
Okay, so that was my first slide. This is the home page for our website from which I've been able to gather information. And this is
TC205 has its own website. This is great.
Yes. And the overall mandate of our committee, sort of summary mandate and scope, is shown on this slide here. So we're focusing on limit state design and geotechnical engineering, load and resistance factor design, development and assessment of design codes, and the impact of natural hazard on safety and serviceability and geotechnical design. So this mandate was established some years ago, before I was the chair. And on the website itself for our page, we have a little bit more granularity on the mission of this TC. So, for example, in terms of dissemination of information. So we want to provide a forum for debate on our mission topics, training information, encourage members to contribute to webinars, such as what we're doing now, and share materials, for example, on random field theory and serviceability limit states, etc. And most importantly, a critical assessment of major design codes. We want to accumulate guidelines and recommendations and publications related to the mandate of our TC205, organize workshops and conference sessions, which we have done recently, and encourage links with representatives from industry, and we're doing that today as just one example. Membership, we have 40 members, and they're divided into members nominated by their national societies and also corresponding members. So I'm the chair, and I am assisted by Fei Han in the United States as the secretary of this committee. Recent activity in the ISSMGE conference, which was held in 2022 in Sydney, we had a virtual session in which four presentations were made by the individuals that are seen on this screen. That was 2022. Last year, we organized a session of papers for the International Symposium of Geotechnical Safety and Risk in Oslo, Norway. And here's a snapshot of the proceedings, and you can see here our session falling below the arrow that I have shown here. And in fact, we actually did organize some other papers as well that went into a session which was organized by TC304. We have organized a 2-hour workshop at the upcoming ISSMGE in Vienna. And at the moment, we have 7 confirmed speakers for this workshop next June. And of course, we're doing this interactive talk. So other things that have happened, the ISSMGE reached out to the various TCs and asked them to nominate a member to appear on the editorial board of the International Journal of Geoengineering Case Histories, which is a journal of our society that has been around for some years. So we nominated Raymond Chung in Hong Kong.
By the way, Richard,
yes,
we're going to have another journal coming up. The new. You have it already. Oh.
I'm ahead of you. I'm well ahead of you. So there's a new journal.
That's amazing.
That has been launched, and again, headquarters reached out to us and asked us to nominate 2 of our members to be on the editorial board, and we have done that, and their names are seen here. So that's the summary of TC205 activities and its mandates.
Fantastic, fantastic.
So now what I'd like to do is just say a few words about some of the research that I've been doing, which falls within the larger mandate of TC205, and that's reliability design and LRFD for reinforced soil structures, with special focus on mechanically stabilized earth. So in North America, we have two design codes for geotechnical engineering. We have the AASHTO code in the States, and we have the Canadian Highway Bridge Design Code. And I have served on the committees for both of these documents, and the contents of these two documents include LRFD design for mechanically stabilized earth. And those sections have been I've made major contributions to. So when I talk about MSC walls, I'm talking about walls which have these, in which the soil in the retained fill is reinforced with horizontal layers of steel or geosynthetic. And in order to carry out the internal stability limit states designs for these MSC walls, we first have to identify what the limit states are. And they are pull-out, reinforcement, soil failure, etc. It's not important for this discussion to get into the details of those limit states. But in LRFD in North America, we identify each design limit state by an equation of the form that you see down here at the bottom, where the nominal resistance is multiplied by a resistance factor, which is 1 or less, and the nominal load term is multiplied by a load factor, which is 1 or greater. And your design has, for each reinforcement layer, has to satisfy this limit state equation. Now, what I've been involved in is the calibration. In other words, what is the value for this resistance factor, given that the load factor is prescriptive? And LRFD calibration is a heavily constrained reliability-based design method. The load factor is typically fixed, and we have to find the resistance factor so that when the limit state design equation is just satisfied at time of design, then the probability that the limit state will not be satisfied is acceptable. And for any other condition, the probability that the limit state will not be satisfied is unknown. We know it's safe, but we don't know how safe or how unsafe. So the motivation for reliability-based design for internal stability of MSC walls, it addresses and quantifies uncertainty at the time of design within a probabilistic framework without the constraints that I've just mentioned. And it provides a more nuanced appreciation of margins of safety than using, simple deterministic factor safety past practice, or load and resistance factor design, or partial factor safety approaches, which are used, for example, in Europe. And one of the outcomes from the research that we have done is that for simple linear limit states, we can calculate using a closed form expression what the reliability index is for each reinforcement layer and for each limit state. And this equation includes quantitatively the uncertainty in the value of the nominal load and resistance at time of design. It also includes explicitly the accuracy of the load and resistance models that are being used in design using bias analysis, where bias is the ratio of measured to predicted, and possible correlations. And this equation, if you look at it closely, if you collect different groups of the statistical quantities that you see there into A and B parameters, what it shows you is that the reliability index varies as the log of the nominal factor of safety that we are familiar with from conventional geotechnical design practice. And this equation is rigorously correct if all of those unknowns, if you like, are log normally distributed, which is a reasonable assumption. In order to assign to the variability in the estimate of the nominal loads in Canada, we use the notion of level of understanding. And so as our confidence in our calculations increases, then the variability in the COV of the nominal load and resistance terms becomes smaller. And remembering again that there's a linear relationship between beta and the nominal factor of safety, an engineer can pick a load model and a limit state. For example, here we have the tensile limit state for the reinforcement in MSE wall, and can, for a target reliability index, say 2.33, which is 1 in 100, he can reach across, intersect the level of understanding curve that they want to design for, high level, typical, low level, and then reach down and touch the horizontal axis that tells them what the minimum nominal factor of safety must be for the design of that layer. And these curves can, yep.
Yeah, sorry to interrupt, but these graphs do exist in the manuals you showed at the beginning?
No. These plots show in various publications that
in papers?
In papers. So the so if you follow my work, this stuff is easy to find, but it provides the framework and examples for engineers who can do these calculations and create these plots themselves.
Are they applied in any software in the market or too early?
No, you don't need to, because they can be generated just using a simple spreadsheet.
Nice.
So for example, that equation that I showed you, you can just dump it into a spreadsheet and do these calculations yourself.
And the COVs you get from the analyzing the data, so reports, all that, or how do you get the COVs?
Well, the COVs for model accuracy, for example, all of that data is available. We have collected measurements from full-scale walls, from laboratory tests, etc., so that we have all of the statistical characteristics for model accuracy for all types of walls and materials. So that these are available, and in fact, there are compendiums of them. In other words, there's a chapter of a book that was recently published by K.K. Poon and Ching, in which we have a chapter, and all of these statistics are available for different MSE wall types and reinforcement types. So it's readily available.
I would like to have a copy or link, because I have MSE walls in a remote area in Nigeria being done, and I like to apply this instead of just plaxes and some hand calculations of limit state.
I will send you later today. I'll send you some papers.
Thank you.
So in conclusion, related to the work that we've been doing, what we're trying to promote is that we should move away from LRFD design in North America and use reliability-based design. It's a much more nuanced appreciation, has much more flexibility than LRFD design. the accuracy of the load and resistance models and uncertainty in the magnitude of nominal load and resistance terms is considered explicitly. And this is the first time that these two types or classes of uncertainty have been combined in an explicit quantitative equation or approach. And we have all of the model bias data available for all of these different types of reinforcement that you see here and for different load and resistance models. And when you use this approach, differences in reliability index are detectable between walls of similar design and between different types of MSC walls performing the same function. So you can do a fair comparison between different design candidates where the differences are described by reliability index. And the interesting and useful thing is that the calculation of reliability index can be done using a spreadsheet using that equation that I showed you earlier. So you don't have to even do Monte Carlo simulation. And very important is that the method provides a quantitative link between conventional factor of safety, which every geotechnical engineer is comfortable with, and reliability index, which is used in contemporary probabilistic analysis and design of geotechnical structures. Up until this point, there were two solitudes. There were the deterministic factor of safety design people, and there were probabilistic people. But connecting them together was difficult and not understood. So this approach combines the two together. And in fact, what we have done in Canada is we have actually, this is a paragraph in the LRFD design manual in Canada that tells people, okay, you can use a reliability theory based approach, even though the design manual is LRFD based. So we are moving forward with this approach in Canada. So that's my short talk, and I'm happy to answer questions. But I think we probably want to move on. So I will stop sharing.
We'll move on. Thank you so much. Innovative and clear. Very nice. And, I like when you simplify things to give important information. Alejo.
Thank you. I am now sharing my screen. I will be very difficult to match what we have just seen. Amazing. So this will be my contribution here. Let me check whether if everything works, because I think so. Yeah. So my pen works. Can you see my screen?
Yeah, great.
Great. Okay. Okay. So of course, aligned with what Professor Bathurst has just explained, I come from the industry. I work at the university and in the industry in SRK Consulting, and we are very busy now estimating the vulnerability of tailings dams, existing tailings dams, and their vulnerability to flow liquefaction, which is a very specific topic. And in doing that, the industry, the mining industry, and the dams engineering industry still using factor of safety everywhere. So we are trying to move away from that. This is the way we try to do that is little by little incorporating what is reliability-based bibliography. And we decided that we will adhere to the principles of Eurocode, which is not LRFD. I mean, I'm one level before, and use the material from Eurocode and trying to use them for tailings dams engineering, which is not a very easy task, but you will see. So in a nutshell, flow liquefaction failure of upstream phase tailings dam is a big issue. Mount Poly 2014, Samar con Fundão 2015, Caria Valley 2018, Corrego do Feijão in Brazil in 2019, Brazil, Canada, Australia in the last few years. This is happening, and it's when what happens when tailings dams, which are dams where the mine waste is deposited, fails due to flow liquefaction, which is a mechanism which is brittle and fails without any warning. The way we are now doing this kind of analysis is essentially using deformation modeling, so nonlinear deformation analysis. And what we do is we start from the very basics of critical state zone mechanics. We have for undrained shear and instability lines, so there is a stable and unstable equilibrium. All of that, all this zone is below the critical state line, but there's a huge difference between one and the other. And if I want to express this for a typical tailings dam, now imagine that this is not one point in the dam, but the full dam, so it's just conceptual. During construction, you build it slowly to some certain point. This is indicative of the state of stress of the dam. And your risk is that that orange dot goes across the instability line into the unstable equilibrium zone and creates liquefaction. Very important for analyzing this is to understand where the peak undrained shear stress and the residual undrained shear stress may lie in your dam. It's not just what happens at each point, but the whole thing. To do this, what we have been doing recently is to pick few triggers, few actions that essentially do nasty things to the dam to see what happens. So we may apply a load at the crest of the dam, and that white arrow shows you the direction where the stress path goes, or we may apply induce some displacement at the top of the dam that will reduce the horizontal stress, and that will be number 2, the arrow number 2, or you may increase the phreatic surface. Those things you do, and what you may do with those is just to create this kind of conceptual 3D graph, and you put the load that triggered flow liquefaction, you put in this axis, and this dot is the load that you computed. Same for water, same for tow displacement. And because these things don't happen by independently, they may happen in a combination. You also check for what happens when you have a small raise in the phreatic surface and a small load, and you end up computing which value creates a triggers flow liquefaction with this combination. When you have all these points here, you can interpolate an analytic. It is an analytic expression of what is called the vulnerability surface. This vulnerability surface is this sort of triangle. So we are assuming by interpolation, because you don't want to do 10,000 finite element analysis. You do few, 6, 9, 12, and you create this interpolated zone. And if you assume that each combination of these 3 actions lying on this surface is a limit state. So this is, for instance, a neat example. So this is the graph of the stress path. It is a movie, but you don't see it. We are increasing the load, and we are computing the maximum load. As we do, both go together, and there is an increase in pore water pressure. A few points here go through the instability lab, not enough to fail the dam. And you can see here in red that a few of these points start to build up, and you see here it's growing. And at some point, this load is lower than this one, because once you reach this load, the progressive failure is initiated, and the thing will go away, whether if you remove the load or not. So it's no longer up to you to remove the load. So you found a limit state here. This is one of the several points that were on that triangle. So what's the contribution of Eurocodes? How do we use Eurocodes here? Well, Eurocodes, in fact, the companion, the support material doing by the Joint Research Center, assembling the ground model, determination of representative values, reliability-based verifications of limit states, implementation of design during execution, and reliability background of the Eurocodes. All of these, plus the Eurocodes themselves, create a bulk of information that we can use to our advantage. How do we apply this to tailings dams? Well, following this method, we start by creating a ground model, which is a representation of the geological conditions in the ground. In tailings dams, because of the way they are built or filled, you always have some layers that were deposited underwater. They are extremely loose, they are very weak, and they are always horizontal because the way you deposit. So you have unsaturated tailings, saturated tailings with some weak layers here. So this ground model means that you may face this sort of failure where you are unlucky and a good chunk of the failure surface goes through one of the weak layers. So you can divide the backscarp where the failure surface, if it develops, will go across all the weak layers, not a long one, and the base where you should expect that the failure surface, if it develops, will go along one of these weak layers. So with the current methods and without developing anything very, very fancy, you are able to spot whether weak layers exist and where they are. But of course, you have to do a serious in situ testing campaign to be able to spot that. So why do we talk about weak layers? Because according to Eurocodes, if you have a geotechnical unit, in this case, the weak layers, that may control the limit state, you must do your best to identify that and to put numbers to it to characterize that. So this brings me to the second thing that Eurocodes bring, which is the old and very well-established statistical analysis of input data. So you start with few data points, and now imagine you only have 5 data points. So according to the statistical analysis that is mandatory, compulsory, you have to use, you end up designing a design characteristic value that is conservative because the lack of enough data means that you are not certain about your mean and your and the statistics of your data. But if you go back and you do more testing and you have more data points, like here, now see that a lot of extra data points, nothing of that will change. In this case, will change the mean value because I faked. I put these data points on top of the previous probability density function to make the mean constant. But because we have more data, the value that we may use for design is not as conservative as previously. This is an easy thing to understand for the people working in civil geotechnics, but in the mining industry, there is the 20% rule or the 30% rule that will tell you that you have few or many data points, you have a distribution, you pick the 20% tail and you use this value regardless the amount of data and the quality of the data. So the contribution by Eurocode is you take into account the amount of data sources, whether it's just CPT or also lab testing or something else, and the quality of the data to get to a characteristic value that is defendable. With this in place, you know that more data allows for less conservatism, which everybody knows, but it's difficult to put in practice within the context of the mining industry. And the third thing that we borrow from the Eurocode's support materials is the concept of the scale of fluctuation, which in the particular case of tailings dams is extremely important because the scale of fluctuation is related to the limit state under analysis or the failure surface. So when you go across or when you go along what could be a weak plane, you have to treat those materials differently. So for instance, we have this potential failure surface. This is the range of potential sliding surface that we are considering. And here, because you cross a lot of weak layers, you cannot be that unlucky that along this line, everything will be weak. So then you are allowed to use something very close to the average strength of this along this line. Not exactly the average because you have few data points. If you had more, you will be moving towards the average. But here, you will probably fail along a weak layer if that exists. So in this case, you will have to use here at the base a cautious estimate that is based on statistics. It's not just engineering judgment. Engineering judgment applies, but it's not what rules. So you end up doing this more or less the kind of thinking that we would have used in the past, with the difference that we have picked this value and we would have applied it to the whole dam. So there is less conservatism in using the Eurocodes in the vast majority of the cases. So Eurocodes produce a defendable set of parameters to feed nonlinear formation analysis. Look at this example from a real case. So here is the box curve, and for average, you have this Andreas strength ratio for residual strength, which is high. And you have here the base, not within the weak layers, but out of them, you have a value of maybe 0.15 in this particular case. It's a real example. And you have two sets of weak layers. You are very unlucky if you go through this, 0.07, not so unlucky if you go through the light blue ones. All this is totally different and way more interesting than just picking a one value for the whole dam. So this is the contribution. And this allows us to work to leave the factor of safety behind and moving towards performance-based risk-informed decision-making. For instance, we can use the material I have shown to compute the probability of failure. So you have the demand, which is the external actions. We have the chances that we will have a load active here, the value of the load, and we must make an estimate of what is the probability of having a certain level of deformation at the toe or changes in the phreatic surface within the dam. Well, that is the demand. And you have the capacity with this, which is the vulnerability surface itself. And now, because these three probability density functions are just analytic functions, and this interpolated surface is also analytic, you can do Monte Carlo exercise. So you pick three values, and if you end up below the vulnerability surface, you are fine. If you are unlucky and above, you have a failure. Well, you do this 10,000 times, it is Monte Carlo, and you compute a probability of failure based on this data. Words of caution. You are estimating the probability density functions of the actions. Your vulnerability surface is fuzzy because you have uncertainty on the strength parameters, and this only applies to the flow liquefaction of one section that you happen to analyze, this is not the full probability of failure of the full dam due to a number of causes. So in a nutshell, a small load acting on your dam, you are okay. A small displacement at the toe, you are okay. But together, they may become a limit state. We are working on this. We are applying this to real world projects, and it is working. It's a lot of discussions. So this brings me to the teaser. To us, ISSMGE, to us, ICOL, to us in the mining industry. From the mining industry, this way, on other ways, the deterministic factor of safety, it is overdue, time to leave it behind. But we need to discuss. From the ISSMGE corner, which is us in this meeting, brittle mine waste requires a little bit of more just thinking that applying standard procedures that are, for instance, LRFD doesn't look good to start with, at least for now. We also need to have a lot of discussions because the operational aspects are controlling the behavior. But we might be in the path of, in a few years, having this, which is fake for now, this kind of booklet that will bring us a reliability-based design and analysis of mine waste storage facilities, combining the experience from the mining industry and ICOL with the kind of expertise and understanding of the problem that we, the members of ISSMGE, have. And this is the final slide of my presentation, Marc. Happy to take questions.
Alejo, thank you so much. You are showing me that we are getting close to understanding how real soil behaves.
Well, I wouldn't say
It's
that.
nice. And I invite you to look at the first ITT talk on tailing dams and mine waste, which shows that all these technical committees we have interact with each other. Thank you so much. If you please like to unshare so that Professor Trevor can share his screen. I really like this lecture, this talk.
Oh, phew.
Trevor, the floor is yours.
Yeah, I'm trying to share my screen now. Workplace. Where was I? My screen. Share. There we are. Oh. How's that?
Perfect.
Can you see my screen?
All yours. Yes,
Okay.
and full screen.
Well, my lecture sort of relates a bit to what Alejo was speaking about. You'll see later on about spatial variability and selection of ground property values for geotechnical design. My background is really my involvement in Eurocode 7 and selecting the appropriate values of ground properties. It's important for ensuring the safety and serviceability of geotechnical designs. And prior to 2010, when the Eurocodes replaced the national standards in Europe, there was no guidance was provided in the different European standards on how to select from test results the values of ground properties for use in geotechnical design calculations. The Eurocodes were established as a harmonized set of standards for structural and geotechnical designs with common rules for all the materials set out in the head Eurocode, EN 1990. And designs are based on partial factors applied to characteristic values. And EN 1990 defines the characteristic value as the value having a prescribed probability of not being attained in a hypothetical unlimited test series. And I'm having problem getting. Yeah, and this value generally corresponds to a specified fractile of the assumed statistical distribution of the particular property. And the only fractile actually given in EN 1990 is the 5% fractile, which is for when failure is sensitive to the variability of the property, as in the case of concrete or steel. Now, this definition of the characteristic value presented a problem for the Eurocode 7 drafters. In geotechnical design, one never has an unlimited series of test results, and only a small portion of the total volume of ground involved in a geotechnical design situation is tested. Also, the characteristic value is affected by the spatial variability of the ground and the extent of the failure surface. And it's been common practice in geotechnical design not to use statistics when selecting ground property values, but to base them on test results together with experience and engineering judgment. So to resolve this Eurocode 7 problem, a derogation was added to the EN 1990 definition of the characteristic value, stating that a nominal value is used as the characteristic value in some circumstances. And this enabled Eurocode 7 not to use statistics in their definition. And a nominal value was defined in EN 1990 as a value selected on non-statistical bases, for instance, on acquired experience or on physical conditions. So the definition then in Eurocode 7, it states that the characteristic value of a geotechnical parameter shall be selected as a cautious estimate of the value affecting the occurrence of the limit state. Now, this definition was very innovative at the time, but it did not provide any specific guidance to the designer. Hence, the question remains when designing to the current Eurocode 7, how cautious is a cautious estimate? So the current Eurocode 7 does say a bit about statistics. According to the current version, it states that if statistical methods are used, the characteristic value should be derived such that the calculated probability of a worst value governing the occurrence of the limit state under consideration is not greater than 5%. And in this respect, a cautious estimate of the mean value is a selection of the mean value of the limited set of geotechnical parameter values with a confidence level of 95%. And then where a local failure is concerned, a cautious estimate of the low value is a 5% fractile. Now, as this is guidance in the Eurocode 7, and it's given us in a note, the implication is that the statistical methods will not normally be used in designs to Eurocode 7, and hence no further guidance is provided on the use of statistics. Now, the second generation of Eurocode 7. In the second generation version of Eurocode 7, which was finalized last year, design properties are obtained by applying partial factors to representative rather than characteristic values. And a representative value is defined as either a characteristic value, and that's one obtained using statistics, so hence it's objective, or else a nominal value, which is a subjective value and based on judgment. And the characteristic value is listed first. So they give you first the characteristic, then the nominal. So the implication of this is that the preferred option in the second generation of Eurocode 7, provided is to use statistics and use the characteristic value, provided sufficient test results are available. And Alejo was talking a bit about the sufficient test results in the last presentation. Now, there's a link here with TC102, site characterization, and they had an IITT, which is published as episode 27. And in this, there were two speakers, Jose Aster and Julia Sorgatz, who gave talks on the selection of ground property values and on the use of statistics in geotechnical design calculations in the second generation of Eurocode 7. And their talks are now on the ISSMGE website, and they provide the background to what I'm about to present. So if we look at the characteristic value then and statistics, the equation given to calculate the characteristic value in Eurocode 7 is that xk, the characteristic value, is the mean value multiplied by 1 minus or plus kn Vx, and Kn was mentioned by Alejo the previous lecture talk, where x mean is the mean property value x from n test values, Vx is the coefficient of variation, and Kn is the coefficient that depends on n and on the fractile required. And the formula assumes that the x values follow a normal distribution. Now, typically, the value of k depends on the type of estimate, whether it's a mean or fractile with the required confidence level, and as well as on n, and hence on the formula for Kn. And if we're talking about type A, the estimate of the mean value, if Vx is known or assumed, then Kn is equal to n95 to the square root of 1 over n, and if Vx is unknown, Kn is t95 n minus 1 times the square root of 1 over n. And then when you're looking at the estimate of the fractile, type B, the inferior or superior values, in other words, the 95 or not 5% or 95% fractiles, Kn is n95 square root of 1 plus 1 over n, or Kn, when Vx is unknown, is t95 n minus 1 square root of 1 plus 1 over n. And n95 is the normal distribution factor for 95% confidence level, and t95 n minus 1 is a student's t distribution factor evaluated for 95% confidence and n minus 1 degrees of freedom. Now, spatial variability has been mentioned, previously, and whether the characteristic value is type A or B depends on the spatial variability. In other words, on the magnitude of the scale of fluctuation, theta, compared to the extent of the failure surface. And when the extent of the failure surface is very large compared to the scale of fluctuation, in other words, when theta over L is approximately equal to 0, the limit state is insensitive to the variability of the ground property, and the characteristic value is an estimate of the mean value, type A. And when the extent of the failure surface is similar to the scale of fluctuation, in other words, when theta over L is about 1, the limit state is very sensitive to the variability of the ground property, and the characteristic value is an estimate of the 95 or 95% fractile value, in other words, type B. Eurocode 7 provides no guidance on what fractile to use when theta over L has an intermediate value between 0 and 1, and that often occurs. And this is termed type C. So we've got these three types of estimates, and a general formula is given by using the ratio theta over L and the sensitivity index, gamma squared is equal to theta over L. And if you use that general formula, Kn is equal to n95, the square root of gamma squared plus 1 over n, when Vx is known or assumed, and when it's unknown, it's T95 square root of n minus 1 square root of gamma squared plus 1 over n. And then putting in the appropriate gamma squared, you see you get when gamma squared is naught, you get the equations for type A, or case A, type A. When it's gamma squared is 1, you get the equations for type B and type C, so those should be types rather than cases. For type C, you get this one, theta over L plus 1 over n, and theta over L plus 1 over n again for the Vx unknown. So if we plot this then, or talk about the scale of fluctuation, due to stratification, the scale of fluctuation of the ground is normally much less in the horizontal scale of fluctuation than the vertical scale of fluctuation. Hence, the vertical scale of fluctuation controls the failure. And published strength profiles show that the average vertical scale of fluctuation for all types of ground is about theta v is 1.35 meters. And using this theta v value to calculate the ratio, the sensitivity index, theta v over LV, we can plot the ratio of the characteristic to the mean value versus the vertical extent of the failure, LV. And you get the plot there. So you see there's the graph for the particular situation of Vx is 0.3, n samples, and theta v is 1.35. And the mean value is here. So that's when xk over xn is equal to the mean, 100% of the mean, of the xk is 100% of the mean. Type A is when LV is infinite, and you've got that, it works out in this example about 85%. So you got that for type A. Type B is when LV is equal to or less than the scale of fluctuation, theta v, and you get this line down here, the lower limit. And between it, you've got the type C. So that shows you how the variation goes from the scale, the extent of the failure surface, the LV along here. And proposed guidance, rules of thumb, on when to use types A, B, and C is to choose the upper and lower limits of those, equal to 10% of the difference between types A and B. So then, assuming theta v was 1.35, the following rules of thumb are obtained for the extent of the failure zone when the different types of estimate are relevant. So type A is when LV is greater than 25 meters. In other words, for example, a slope. Type B, LV is less than 2 meters. In other words, be a small foundation, small spread foundation, or maybe the base of a pile. And type C, when LV is between 2 meters and 25 meters. In other words, for the side of the shaft friction on a pile foundation. And then plotting it here on a graph showing these boundaries. So we've got the type A analysis, and that's when we got to see the 10% of the difference between type A and B down below type A, you've got that limit there. So type A goes from 25 up to 40 or above 25 and above. So that's the type A range. Then the type B range is over here when you've got the limit, the 10% above type B, that's the limit for the range for the type B. And so the extent of it is 0 to 2 meters. And then in between, you've got type C. So these are the type C from 2 meters up to 25 meters. So that gives you how sensitive the critical value is, the characteristic value is, and what values you should choose between either 50% or 80% of the mean value. So recently, TC304 engineering practice for reliability and management had an IITT episode 26. And in this, Professor Mike Hicks discussed spatial variability as one source of uncertainty, and we also discussed the scale of fluctuation and how they affect geotechnical analyses. And this talk is also now on the ISSMGE website. So some concluding comments. The second generation of Eurocode 7 will require much greater use of statistics. It'll provide practical guidance on the selection of property values using statistics, and it will replace the existing Eurocode 7 on the 31st of March 2028. So second generation coming in on that date. And then the guideline document, which was mentioned by the previous speaker, there are 5 of them, but this is the one that I was particularly involved in. The JRC European Commission has published they're free on the website, guideline on the determination of representative values from derived values for verification with limit states with EN 1997. So you can find out some more about the selection of representative values from that guideline. So that's the end of my talk. Thank you.
Very, very interesting, Trevor. Nice analysis, straight to the point, and the best marketing for the IITT, referring to the other previous
It's nice to see
one.
them linking together. Yes.
They are all linked. So for our viewers, we are doing those IITT to cover almost, if I can, before I leave the presidency, all the technical committees, subspecialties of geotechnical engineering. We have about 40 of them.
Yeah.
40 technical committees. Sumanth, are you ready?
Yes, sir, I'm ready.
Trevor, if you unshare your screen this way.
Top chair, yes.
I like this picture. Where was this taken? Which lake?
Glendalough. Do you know Irish lakes? Near Dublin.
Nice. I want to go there and do some hiking. It's beautiful.
Indeed. It is nice there.
Sumanth, the floor is yours. We have to be brief because we're running out of time.
Yes, sir, sure. I won't take much of your time. So can you see my screen?
Excellent. Or ears.
So, hello guys, myself Sumanth, and it's my first interactive talk in ISSMGE, and I'm very excited about it. Today, I would like to talk about the role of geosynthetics, as the geosynthetics are very cost-effective, durable. So how it affects it? Let's see. So it's the stage. Every geotechnical design is evaluated against 2 primary criteria. First, we have ultimate limit state, and the second, we have serviceability limit state. We all well known about it. And in the ultimate limit state, where it will be focused on sliding, deep-seated failures, and settlement. In the serviceability state limit, we'll focus on seepage, tilting, and vibration. Now, let's see the case studies. I have 3 case studies here. So let's see. In the first case study, the Transcona grain elevator built in 1933. It is a textable example of USL failure. Here, as we can see, the structural integrity is good, but the geotechnical part where it fails. It sank a dramatic 27-degree tilt and sank 30 feet into the ground. This was an ultimate bearing capacity failure. Here, the engineers relied on inadequate shallow soil testing, completely missed the highly compressible clay layers resting deeper below. Fortunately, as we discussed, structural integrity of the reinforced concrete prevented the beams from shattering. Engineers were able to recover the structure using hydraulic jacks. Now, the case 2. As we well know, Leaning Tower of Pisa is a failure of settlement. The foundation focus, the shallow, it is a it's focused on shallow foundation, weak and high compressible marine clays. By 1990, it was tilted up to 5.5 degrees still, and uneven shaking occurred. After that, the engineers stabilized it by carefully extracting soil from north side to pull it back towards the center. Now, what happens if the Sorry. Now, what happens if the failure happens in both safety and serviceability? That's what happened here while constructing a retaining wall here. So here both the safety and serviceability is failed. When we fail to respect both safety and serviceability, these kind of strategy strikes. As you can see here, before and after the collapse, both safety and serviceability both are failed here. And to prevent these kind of tragedies, we have a lot of engineering aspects, a lot of methods to stabilize the soil. As you can see, geosynthetics, soil nailing and anchors, all are here. But why geosynthetics? This is the main question we can ask. It's like geosynthetics is very cost effective, durable, and it's a sustainable solution. And it's easy to install sometimes. So here, this is one of my work. In Plaxis 2D, I designed a model of height 9 meters and the length of the road embankment. I considered a road embankment. The length of the road embankment is 6 meters. So I designed I designed the embankment with I considered 2 embankments with 1.5 vertical with a slope of 1.5 vertical, 1 horizontal, and 2 vertical, 1 horizontal. That is toe failure. That resembles toe failure and weak foundation soils with greater slopes. 2 vertical, 2 horizontal, 1 vertical, and 3 horizontal, 1 vertical. It shows base failure. So here I used two-part wedge analysis by Wood and Jewell to guarantee ultimate limit state. Accounts for complex interaction between active and passive soil wedges. Here, as you can see, without any geogrids, the failure surface looks like this. But after applying geogrids, the failure surface has been decreased, as you can see. It is for 1.5 vertical to 1 horizontal slope. So here the placements of geogrids were done by Eurocodes and FEMA. How much tensile strength is needed for these geogrids? We take the maximum tensile strength for these geogrids. And also, as you can see, 2 vertical to 1 horizontal for the slope. For the slope, this is the failure surface with and without geogrids. But in the soft soil, we use geocells. Why? Because geocells have more tensile strength compared to geogrades. So this is the failure surface with and without reinforcements. As you can see, with geocells, the failure surface was drastically reduced. What are the conclusions? What are the frame results and the interfacial factors? We reduce the interfacial factors perfect 1 to 0.6. Unreinforced steep slopes show dangerously low factor of safety, predicting immediate toe failures. Optimized the placement of geogrades using limit equilibrium analysis and Federal Highway Administration. Geogrids act
Sumanth,
as, sir.
the geocell you're using are those weaving like lozenges?
Yes,
How
sir. It's
thick
a
are you
3D structure.
using? You
3D
know they
structure.
can reach how thick?
Sir?
The height of the cell?
Height of the cell, it's
The one you're modeling here.
yes, sir. Yes, sir. Sir, I took a layer of 2 meters, sir.
2 meter?
Yes.
In the market, I think they reach 1.2 meter geocell. I don't know if
No, sir.
tensar maybe.
Yes, sir. Yes, sir. I took the soil layer, sir, not geocell. This is the soil layer. This is the
Oh,
soft
I
soil
heard,
layer, sir.
yeah. Okay.
Yes, sir.
I
This is the
thought you're
hard soil.
comparing geogrids with geocells.
No, sir. I'm just comparing.
Okay.
This is the soft soil, sir. This is the soft soil, and I increased the soil bearing capacity. I mean, this is the
So you're
uh,
comparing between strong base and soft base,
yes, sir. Yes,
different angles.
yes, sir. So I took an angle of 53 degrees, 60 degrees, and 22 degrees and 18 degrees, sir. These are the steep slopes. Yes, sir. These are the steep slopes. So achieving serviceability and conclusion. Evaluated the serviceability limit state by closely monitoring total incremental displacements. The displacements are also decreased by using the geocells and geogrids. I applied a surcharge load of 20 kPa, suffered that to resemblance the real characteristics of how the road works. And geogrids physically locked soil particles, drastically reducing total displacements. So I just want to uh, say that geogrids nowadays, many of the projects are going to use geogrids and geocells. So it's better to go geogrids as it is more reliable solution. Thank you.
Suman, thank you. I
Thank you,
like
sir.
that you clearly show when the soil is soft, the failure is deeper. So be careful. Don't
Yes, sir.
go, don't mess with
Yes,
that
sir.
soil.
Yes, sir.
Guys, thank you so much.
It's
I
my
don't know if
pleasure.
you want to add anything. This lecture or episode will be released in a week or so.
Okay.
Thank you very much for your time, for preparing and being with us. Um, it seems from what I'm receiving, we're gonna have a busy night in Beirut. So
Have a safe
Take
night, sir.
care. Take care.
Mm-hmm.
Take care.
thank you
Very good.
guys
Be
and
safe.
wish you the best.
Yeah.
Bye.
All the best.
Bye.
Ciao,
Thank
ciao.
you. Thank you.
Bye.
It's a pleasure, sir. Thank you.
My pleasure, Suman.